Okay, so what happens if you take a loop that's not a circle? What if you put it in any shape you want? And in fact, you don't even have to put the loop to be in one plane. It could be coming out of the plane and going, as long as it's just some contour in space. And you take integration of B dot ds around that contour. What does the value give you? Well, you can prove it, and we're not going to do the proof here, but it'll give you also mu naught times I. And so that's where the usefulness of this rule comes. It's the same way Gauss's law was useful. We found it's useful. It's something that's always valid. Well, this turns out to be always valid. We're going to show later on that Ampere's law, you have to add to it another term, but in the cases that we're talking right now, we don't need to, and the right-hand side is just mu naught times I. So this is kind of analogous to the case where we took a Gaussian surface of any shape. Remember, when you took a Gaussian surface of any shape, the flux through it was just Q over epsilon node. That's it, and it didn't depend on the shape. Well, the same thing here. It doesn't depend on the shape of the contour. Integration of B dot ds is always mu naught times the current enclosed. And in this case, when you take the ds vectors and you put your fingers around the ds vectors, the thumb points in the same direction as the current, and so that means the right-hand side is positive. So that's how you can get the sense of the right-hand side to be positive, by this right-hand rule. Okay, what if you take the ds vectors going the opposite direction? So now when you put your fingers around the ds vectors, your thumb will point downwards, opposite the current, and that's when you get a minus sign. And the reason is because in this case there will be more cases than that when the magnetic field will be opposite the ds vectors, and you're going to get a minus sign in the end. So you can prove it, but we're not going to prove it. We're just going to take it to be a given. So to get the sign of the integration, if integration of B dot ds is positive or negative, you put your fingers in the direction of ds. If your thumb is in the direction of the current, then you put a positive. If it's opposite the direction of the current, you put a negative. And this case where you get a negative is analogous in some sense to the case where you have a negative charge inside a Gaussian surface, and the electric flux turns out to be negative. It's the charge inside over epsilon node. It's a negative value of charge. Here again the same thing. When you put your fingers around ds this way, you get the thumb pointing downwards. It's opposite current, so you get a minus sign here. So this is a sense of the current enclosed is negative. And what happens then if you put the loop in a place where the current is not going through the loop? So the current here is not enclosed. What do you think the integration of B dot ds will be? It's zero. It will turn out to be 0. And it doesn't matter in that case if you take ds that way or this way. It doesn't matter. It'll just be 0. As long as there's no current enclosed, the current doesn't go through the loop, then you get a 0. And just to get an idea how that can happen, where does this cancellation happen? How can you get something when you add up the dot products of all these around the loop, you get 0? Where does this cancellation happen? Think of it this way. Remember that the magnetic field lines, due to an infinite wire, they go around in circles. So here the magnetic field is going this way, but over here the magnetic field is also going that way, but it's a bit weaker. So you can see here in this region, the B and ds are opposite each other. So you're going to get quantity dot products that are negative. Here, the ds and B vectors are in the same direction or close to the angle is less than 90 degrees. So you get a positive contribution. So that's why when you add all these positive contributions with these negative contributions, you're going to get 0. We didn't do the proof, but you can prove it, and it turns out to be 0 exactly. So this issue where the loop is not enclosing any charge, or the current is not going through the loop, it's analogous kind of to the case where you have a surface, a Gaussian surface with no charge enclosed, and the charge is outside. Remember, in that case, the total electric flux through this closed surface is 0, because when the electric field line goes in to the surface, it went in with a negative contribution. When it goes out with a positive contribution. And these two contributions cancel out exactly. And so the total flux is 0. Same thing here, same idea. If the current is not enclosed inside the loop, then when you get integration of B dot ds, you get 0. And we saw in the previous slide how this summation gets to 0 in an intuitive sense. We didn't do it exactly, but we did it in an intuitive sense, that here you get negatives, Here you get a bit positive. When you add them all, you get 0. So this is the statement then of Ampere's law in the general case. Let's say you have a general loop like this, and the loop doesn't have to be in the same plane. It could be going out, and it doesn't have to be in one plane. And the currents don't have to be infinite lines, straight lines. They could be any kind of current of any shape. But the important thing is that they have to be enclosed. We have to differentiate between currents that enclose the loop, they go inside the loop like these two, and currents that don't go through the loop like this one. So I1 and I2 will contribute to integration of B dot ds, but I3 will not contribute. And so to find out if this contribution is going to be positive or negative, remember, how do we do that? We use the right-hand rule. So we put our fingers in the direction of the ds vectors. The thumb will point upwards. It'll point upwards for both cases. So you can see here that the thumb is in the same direction as the current, and so you get a positive for that. The thumb here is opposite the direction of the current, and you get a negative. So then the integration of B dot ds will be mu naught times I1, positive quantity, minus mu naught I2, negative quantity. So that's how you can get the contributions if they're positive or negative. And then there's nothing for I3, so you have 0. There's no here contribution from I3 because I3 is not enclosed in the loop. So you only put the currents enclosed inside the loop. What happens if you take a wire and it goes through the loop here, and then it goes up, and then it goes through the loop again, but in the opposite direction? Well, when it's going through this way, it goes through with a positive sense. When it goes through this way, it goes through with a negative sense. And so they cancel out exactly, and you get, as you expect, you get 0. Okay, so this is again the summary of the Ampere's law. Integration of B dot ds is equal to mu naught times the current enclosed. Remember what in current enclosed means that the loop of the current wire has to go through this area that that encloses this loop. If this loop is not in one plane, then this surface will be a bit more complicated, and we're going to see later on which surface do we mean in that case. You can take any surface actually, but as long as the surface completely encircles the loop. And then the positive sense for the current, if you do the right-hand rule, put your fingers in the direction of ds, your thumb, if it in this case it'll point upwards in the direction of I, so you get a positive contribution. Here you get the thumb upwards, opposite the current you get a negative. This one is outside, it doesn't enclose the loop, so you get a 0 contribution, doesn't contribute at all. If you want to write down the current enclosed in a more professional way or a different way, remember current through any surface is integration of j dot dA. But if you do that, you need to specify what the direction of the area vector is. And you do that by the right-hand rule. If you put your fingers in the direction of ds, the thumb points in the direction of the dA vector. And then in that case you can see how you get the positive for this case, because in this case when the current goes upwards, j is upwards, so the dot product between j and dA is positive, so that's why you get positive. When you have dA here upwards, but here the current is going down, then GA is going down, then the angle between dA and j will be bigger than 90 degrees and you get a negative. So writing the law this way, you have to define the sense of the relationship between ds and dA. If you put your fingers in the direction of ds, your thumb will point in the direction of dA. So they have to be related this way for this equation to work correctly. We're not going to use this much in this way. We're going to use it in just the way that we did before, but it's nice to know how you can write it down in a more professional way. And it's clear here when you write it this way that you're only taking the current enclosed because integration of j dot dA is being done over this surface. So of course this current will not contribute to this integration because it's not going through the surface.